Hey you guys, we are in Chapter 2, Section 1, and we are looking over patterns and inductive reasoning. We do have 3 objectives to cover. We are going to find and use a pattern, we're going to make conjectures regarding the continuation of patterns, and we're going to find a counterexample. Alright, so Objective 1 is to find and use a pattern. So when you look for a pattern in a sequence, you want to look for a relationship between the terms. And you want to test that that relationship is consistent throughout the entire sequence. So in our sequence, we go from 3 to 9, 9 to 27, and 27 to 81. When we have a numerical pattern like this, or a numerical sequence, the pattern is typically going to be some kind of operation, addition, subtraction, multiplication, or division. Sometimes it's going to be a combination of patterns, but you want to start with the simplest. So the simplest here would be adding. So from 3 to 9, if we add 6, we get 9. From 9 to 27, we wouldn't be adding 6. In this case, we'd be adding 18. So we might not have a pattern there. We can see from 27 to 81 what we would be adding. And we see that we're adding 54, and we might see a pattern in the numbers that we're adding and how they're getting bigger, but there might be a simpler pattern. So instead of adding, let's move to multiplication. From 3 to 9, we have to multiply by 3. From 9 to 27, we're multiplying by 3. And from 27 to 81, we are multiplying by 3. So this might be the easier pattern. So in order to find the next 2 terms in this sequence, all we have to do is multiply by 3 again, and we get 243. And when we multiply this by 3, we get 729. Alright, so let's look at B, problem B. So here we want to identify the next 2 terms in our sequence. And we see that we have a circle in each of our shapes, but then the shape inside, the polygon inside, we have a triangle, and then it appears to be a square, and then it appears to be a pentagon. And we see that we go from a shape with 3 sides to a shape with 4 sides to a shape with 5 sides. So this pattern is pretty easy to identify, and I know that my next 2 shapes, or my next 2 terms in this sequence, I'm going to have a circle, and this time I'm going to have 6 sides. So 1, 2, 3, 4, 5, 6. And yeah, that's not the prettiest, but you have to get over that. And the next one is another circle, and instead of 6 sides, I'm going to have 7 sides. So 1, 2, 3, 4, 5, 6, 7. Again, not the best, but maybe if I was using paper and pencil, it might be a bit nicer. So I want you to try below to find the next 2 terms in the sequence. So take your time to identify the pattern, and then show me the next 2 terms in each A and B. Alright. Our second objective is to make conjectures. Now, you may want to find the 10th or the 100th term in a sequence. And instead of going all the way from the first term to the 100th term, we would want to try something else. So in this case, rather than find every previous term, you can look for a pattern and make a conjecture. Now, a conjecture is a conclusion you reach using inductive reasoning. So we're going to write here that a conjecture, that's an E, is a conclusion you reach using inductive reasoning. So inductive reasoning, for those of you who may have forgot from algebra, inductive reasoning is the process really where a small observation that you might make is used to infer a larger theory without actually proving it. So what we're going to do is we're going to take what we see in our examples and we are going to reason based on just what we see. So in this example it says, what conjecture can you make about the number of regions 10 diameters form? I'm sorry, not 10, 20 diameters. So in our picture we see that we have one diameter, so one diameter here, it forms 2 regions. And then we have 2 diameters and we have 4 regions. And then we have 3 diameters and we have 6 regions. And we want to see the pattern between diameters and regions. So from 1 to 2, from 2 to 4, and from 3 to 6. Now again, when you're looking for patterns, it's usually some kind of numerical operation, addition, subtraction, multiplication, division, and it also could be a combination. So you should hopefully realize that each time we are multiplying by 2. 2 times 2 is 4, 3 times 2 is 6. So the conjecture that we can make is that 20 diameters will form 40 regions. So 20 diameters will form 40 regions. In the second example, In the second example, it says, what conjecture can you make about the 21st term in RWB? So we want to find the 21st term, and we have 3 terms that are being repeated, RWB, RWB. Well, since we have 3 terms, and the 21st, or the number 21, is actually a multiple of 3, then we know that we have our pattern RWB, that pattern, let me write it out, RWB, we have each of those 7 times, right? So we could say, 1, 2, 3, 4, 5, 6, and we have this 7 times the RWB to get to the 21st, since we have 3 terms and 21 is divisible by 3 to 7. So if we want to know the 21st term, well, that's going to be our 3rd term here, which is B. So B is a conjecture I can make about our 21st term. Alright, so you guys try, oh, I'm lying, I got one more example, and then the you tries below. This one says, what conjecture can you make about the sum of the first 30 odd numbers? So the first 30 odd numbers, what conjecture can we make? So what I'm going to do first, and what I suggest you to do, is to make a table, kind of just to see what the first few sums are, so we can see what the pattern is. So we are using the first 30 odd numbers. So the first odd number is 1. Oops. It's 1. And if we add that to nothing, we get 1. Then we can add 1 plus 3, because 3 is the next odd number, and we get 4. Then we can say 1 plus 3 plus 5, the next odd number, and we get 9. And you might see the pattern already. I have an idea, but just to make sure, I'm going to add the next odd number. So 1 plus 3 plus 5 plus 7, and I get 16. So hopefully you see this pattern. In this case, it's not a pattern of addition, subtraction, multiplication, or division, or a combination. It's actually a pattern dealing with exponents. So the first term is actually 1 squared. Our second term is 2 squared. Our third term is 3 squared. Our fourth term, I guess I should be saying these are equal to. Our fourth term is 4 squared. So now that I see that pattern, the conjecture I can make about the sum of the first 30 odd numbers, well, I know then that that would sum to 30 squared, which is 900. All right, so now here are your 2 U-tries. Going to try these out. Hopefully these are a little similar to the ones that we just went over, and then continue on to the next slide. All right, our last objective is to find a counterexample. So not all conjectures turn out to be true. You should test your conjecture multiple times. You can prove that a conjecture is false by finding just one counterexample. And counterexample is one word, but I'm not going to fit it in that small space. A counterexample is an example that shows that a conjecture is incorrect. So again, this space is counterexample, which is again one word. All right, so A, B, and C will go over together. It says, what is a counterexample for each conjecture? So we just need to find an example that proves the conjecture false. So A says, if the name of a month starts with the letter J, it is a summer month. So all we have to do is think of a month that starts with the letter J that is not a summer month. And that's it. So January is not a summer month, but it starts with the letter J. So there's our conjecture, or I'm sorry, there's our counterexample. So that one wasn't so bad. Let's look at B. It says you can connect any 3 points to form a triangle. So we know that's not true always. Our counterexample, this time I'm going to show a picture. I'm going to have 3 points that are collinear. So here I have connected 3 points, and I cannot form a triangle because they are collinear. So here's my counterexample, and I can write that out in words too instead of just giving a picture. I can say if the 3 points are collinear, then they cannot form a triangle. And the last one says, when you multiply a number by 2, the product is greater than the original number. So when you multiply a number by 2, the product is greater than the original number. So this might take you a while to figure out, but if you only think about the positive numbers, then that might be true. Maybe you could think about fractions or negative numbers. So if my number is -1 and I multiply that by 2, then I get -2. And -2 is not greater than, so here's a greater than sign with a line through it, than -1, the original. So here's my counterexample, and I'm not going to write this one out in words. I'm just going to show my example as my counterexample. All right, so I have 3 for you to try. Find the counterexample for each. And that's it. So with these notes, I'm going to grade these based on whether or not you did all of the U-tries and if you have notes as well. So you need some notes here also, in addition to all of your U-tries. All right, I'll see y'all in class. Thanks.